Earth Systems 3209. Unit 3, Earth's Materials. Unit 3 references can be seen in Chapters 2, 3, 6, and 7, and Appendix A and Appendix B. Unit 3, Topic 1.3. This topic will discuss mineral properties. We will focus on identifying the 3 characteristics that all mineral properties depend upon, and also we will focus on identifying and describing which mineral properties are most reliable when identifying minerals. When we look at mineral properties, each and every mineral property has certain properties. The properties of each mineral depends upon, number 1, the type of elements present, number 2, the arrangement of the atoms, and number 3, the strength of bonding. Text references for mineral properties can be found on pages 40 to 44 in the textbook. The following are a list of physical properties that each mineral may display. Number 1, specific gravity. 2, hardness. 3, streak. 4, cleavage. 5, fracture. 6, luster. 7, crystal shape. 8, color. 9, taste. 10, feel. 11, magnetism. 12, acid test. And 13, fluorescence. Out of 13 of these physical properties, the first 4 are your most reliable, and these are the properties that will be discussed during this presentation. Let's look at the first physical property, specific gravity. Specific gravity is the mass of a mineral compared to that of an equal volume of water. To determine specific gravity, you need to carry out the following 3 steps. First step, weigh your specimen in air and record the weight. As you see in the diagram to the right, we have a spring scale that basically weighs the specimen in air. You can also do this today using a modern digital scale. Second step, weigh the specimen submerged in water and record the weight. Again, the diagram to the right shows that the specimen is now submerged in a beaker of water and the corresponding weight is recorded. Once you get the weight in air and weight in water recorded, we can calculate specific gravity using the following formula. Your specific gravity is equal to the weight of the mineral in air divided by the weight of the mineral in air minus the weight of the mineral in water. When we look at specific gravity and Core Lab number 4, which was completed during the course, we notice that specific gravity is equal to density. And these 2 properties are equal because pure water at 4 degrees Celsius has a density of 1 gram per cubic centimeter. The specific gravity is equal to the density. Thus, to determine density, you will need to do the 3 following steps. Use a scale to measure the mass of the mineral. This can be done on a digital scale or a spring scale. Number 2, find the volume of the mineral sample. We usually find the volume of the mineral sample by a process called water displacement, where you may have a graduated cylinder with a certain volume of water within it, and then you slowly place the mineral sample in the graduated cylinder and see how much the water rises. The level to which the water rises will be the new volume of the mineral. And if you take the rise volume minus the original volume, that will give you water displacement, which is the volume of your mineral. And third step, we calculate the density using the formula density equals the mass of the mineral divided by the volume of the mineral. Also in the core lab number 4, we noticed that 1 milliliter of water, which is equal to 1 centimeter cubed, is equal to 1 gram. Therefore, 1 milliliter of water weighs 1 gram. So if we know the weight of an equal volume of water in grams, we can use the following formula to calculate specific gravity, which is really equal to its density. Let's look at the following calculations. If, for example, we take the first example here, we know the weight of a mineral sample weighs 750 grams. So the mass of the mineral is 750 grams. If we take each of these two samples and displace it in a graduated cylinder of water, it was noted that the equal volume of water will be 100 milliliters. And seeing that 1 milliliter weighs 1 gram, then 100 milliliters would weigh 100 grams, as seen in the diagram here. So the weight of the water, equal volume water, would be 100 grams. So from these measurements, we can calculate the specific gravity of water by calculating density. We use the formula specific gravity equals the weight of the mineral divided by the weight of an equal volume of water. In this case, the weight of the mineral was 750 grams. If we divide that by the weight of an equal volume of water, which is 100 grams, we will end up getting the specific gravity of the mineral, which is 7.5. So the weight of the mineral divided by the weight of an equal volume of water will give you the specific gravity of the mineral. And in this case, our specific gravity was 7.5. Let's look at a second example. If we look at the second example down below, we notice that the mineral sample weighs 250 grams. Again, when we displace this in a graduated cylinder full of water, we notice that it displaced 100 milliliters of water. And because 1 milliliter of water weighs 1 gram, therefore 100 milliliters of water will weigh 100 grams. So to calculate the specific gravity of the second example, we know the weight of the mineral was 250 grams. Divide that by the weight of the equal volume of water, which is 100 grams, and we obtain a value of 2.5. So the specific gravity of the second example was 2.5. So what that actually means is that the mineral sample weighs 2.5 times greater than the equal volume of water. And for the first sample, which had a specific gravity of 7.5, that means that the sample is 7.2 or 7.5 times heavier than the equal volume of water. And this can be seen here to the right of the diagram. Let's look at a second mineral property. This mineral property is called hardness. And hardness is the resistance of the mineral to scratching. So how hard a mineral is depends on how much it resists the ability of it to be scratched. Hardness is expressed in terms of Mohs hardness scale, which ranks relative hardness from 1 to 10. If you want to remember Mohs hardness scale, which is located in the diagram here to the right, we can use a rhyme to remember the hardness scale. So let's look at the hardness scale first. Mohs hardness scale states that minerals were ranked in order from 1 to 10. So Frederick Mohs collected a whole wide variety of minerals, and he tested the relative hardness of one mineral against another. When he had all the minerals ranked from softest to hardest, he then took 10 minerals that were fairly common, and he ranked them, or he assigned them, an arbitrary number, relative hardness to one another. The mineral that he assigned a hardness of 1 was called talc. He assigned a hardness of 2 to gypsum, a hardness of 3 to calcite, a hardness of 4 to fluorite, a hardness of 5 to apatite, a hardness of 6 to orthoclase feldspar, a hardness of 7 to quartz, a hardness of 8 to topaz, a hardness of 9 to corundum, and a hardness of 10 to the hardest known mineral known to man, which is diamond. So if we had to memorize these minerals on Mohs hardness scale from softest to hardest, we could use a rhyme. Again, the first letter in the rhyme corresponds to the first letter in the name of the mineral. The rhyme that I use in class is, tonight gypsies come from Africa on quads to catch dinosaurs. The corresponding letters in this phrase, T in tonight represents talc, G in gypsies represents gypsum, C represents calcite, F fluorite, A apatite, O orthoclase feldspar, Q quartz, T topaz, C corundum, and D diamond. So again, you can make up your own rhyme to help memorize the minerals on Mohs hardness scale, or you can use the one that I have stated here. When we look at hardness, we generally find the hardness of minerals using common objects. The following objects can be used when trying to determine the hardness of different minerals. If the object scratches the mineral, then it is harder than the mineral. For example, the objects we usually use in a laboratory would be your fingernail, which has a hardness of approximately 2.5, a copper penny, which has a hardness of 3.5, an iron nail, which has a hardness of 4.5, glass, which has a hardness of approximately 5.5, and a steel file, which has a hardness of 6.5. If one of these objects scratches the mineral sample, then it is harder than the mineral sample. For example, if we look in the diagram, we notice that a person's fingernail is used to scratch the mineral sample. Therefore, the mineral sample must be softer than the hardness of the fingernail. And your hardness of your fingernail has the value of 2.5. Therefore, the sample must be less than 2.5 because it can be scratched by the fingernail. If we go and look at an iron nail, if you use an iron nail to scrape across a mineral sample, the iron nail has a hardness of 4.5. If it leaves a scratch in the sample, then the sample must be less than 4.5. If the nail does not leave a scratch in the sample, then the mineral sample would have a hardness of greater than 4.5. Another test we could test on is glass, which has a hardness of approximately 5.5. So if the glass scratches the mineral sample, then the mineral sample is less than 5.5. But if the mineral sample scratches the glass, then the hardness would be greater than 5.5. So in review, when we look at finding the hardness of a mineral, especially if it's a non-known mineral, we use our fingernail, a copper penny, an iron nail, glass, or a steel file. And by using these objects to scratch the mineral sample, we can obtain a hardness, a relative hardness of the mineral sample. If the steel file don't scratch the mineral sample, then we just say that the mineral sample is harder than 6.5. A third mineral property that we can study that is very reliable is called streak. Streak is the true color of the mineral in its powdered form. And to perform a streak test, you take the mineral and scratch it across non-glazed porcelain tile, as seen in the diagram here. Once you scratch the mineral across non-glazed porcelain tile, you will notice that there is a powder left on the tile, if the mineral is softer than the unglazed porcelain tile. This color of the powder is the true color of the mineral. If you do not see a streak left behind on the unglazed porcelain tile, then the mineral may be harder than the porcelain tile and may not leave a streak. Or the powder left behind could be the same color as the tile. So you may want to rub your finger across the porcelain tile and see if there's a white powder left behind. And if there is, then the true color of the mineral would be white. A fourth property that we use to test for unknown mineral to help identify minerals would be cleavage. Cleavage is a tendency of some minerals to break along smooth, flat, parallel surfaces. Two properties that minerals' properties depend on would be the atomic structure and the strength of the bonding between the atoms. These two properties determine how a mineral will cleave. Cleavage directions are determined by atomic structure and the strength of bonding. So the tendency of some minerals to break along smooth, flat, parallel surfaces, that is cleavage planes, will depend on how the minerals are bonded together and the arrangement of the minerals within the atoms, between the atoms. Cleavage follows areas of weak bonding. So if we look at the diagram below, we see that in this diagram we have layers of atoms all bonded tightly together. But in between the layers of the atoms, we see the yellow dots, which represent a weak cleavage plane. This area of weak bonding basically will help the mineral split along smooth, flat, parallel planes, which will form a cleavage plane. Minerals show cleavage in many different directions, but most common are planes of 1, 2, and 3 directions of cleavage. So cleavage in one direction is the type of cleavage we call basal cleavage. An example of a mineral that displays cleavage in one direction would be mica. If we look at the diagram below, we see that layers of atoms have weak bonding areas in between. Along these weak bonding areas, we see the minerals can split easily. And this is demonstrated in the diagram to the right, where we see a person pulling off layers of mica atoms, basically exhibiting areas of weak bonding in one direction. So therefore the mineral will split off in layers if it has weak bonding in one direction. When we look at cleavage in two directions, we see that weak bonding can occur in two different directions. In the diagram below, we see two planes of cleavage represented by a yellow line and a red line. So in this diagram, the yellow line represents a horizontal cleavage plane, whereas the red plane will indicate a vertical cleavage plane. On the end of this mineral, there is no cleavage planes, which ends up in the mineral fracturing. So if we look at the sample to the right, we see two flat planes. Each of these planes would represent a cleavage surface. So feldspar, orthoclase feldspar in particular, would have cleavage planes in two directions. Cleavage planes in three directions. This is represented in the diagram below. We see three planes of cleavage. And each of these planes of cleavage are located at 90 degrees to one another. We see a vertical plane of cleavage represented by the yellow plane, another vertical plane of cleavage 90 degrees to it represented by the blue plane, and a horizontal plane of cleavage represented by the red plane. If we look at a common example of a mineral that exhibits this cleavage, that would be halite, which tends to split along smooth, flat, parallel surfaces, which are cleavage planes, in three different directions. Therefore, they form cubes. And halite, which is table salt, would exhibit this type of cleavage. They split in three directions, which represent cubes. Let's look at some common examples that were taken from past public exams. First question reads, what is the approximate hardness of an unknown mineral if it can be scratched by a copper penny, but not by your fingernail? So the main points in this question include that it can be scratched by a copper penny, but not by a fingernail. Therefore, if we look at being scratched by a copper penny, the copper penny has a hardness of 3.5, whereas your fingernail has a hardness of 2.5. So therefore, the hardness must be greater than your fingernail, but not as hard as a copper penny. So it would be between 2.5 and 3.5. So the answer to this case would be B. Next question says, how many cleavage planes are visible in the mineral sample to the right? So if we look at this mineral sample to the right, we notice that we see each individual part. We see three cleavage planes. And each of the three cleavage planes are located 90 degrees to one another. So our answer for this question would be A, three cleavage planes. Notice that there are several different surfaces that exist in the same plane. For example, the tops are three different surfaces, but they're all in the same direction, so they all have the same cleavage plane. The fronts, again, three different surfaces, but the same cleavage direction. So the answer to this example would be three cleavage planes. Example number 2 reads, a mineral sample with a mass of 75 grams is placed in a graduated cylinder with 100 milliliters of water. The water level rises to 125 milliliters in the cylinder. What is the specific gravity of the mineral? So if we look at this question, the information given says the mass of the mineral sample is 75 grams. So we know the mass of the mineral. Is 75 grams. We also know that there was 100 milliliters of water placed in the graduated cylinder, and the water level rose to 125 milliliters when the sample was put in. So if we want to find the volume of the mineral sample, we take 125 milliliters and subtract from it 100 milliliters, and that will give us 25 milliliters. So if we want to find density, density equals the mass of your mineral sample divided by the volume of your mineral sample. And in core lab number 4, we recognize that volume of the mineral sample is also equal to the mass of an equal volume of water. So for this case, we can see that 75 grams divided by 25 milliliters in this case, but we notice that 1 milliliter equals 1 gram, so this would be the same as saying grams. And this will correspond to an answer of 3.0 grams per milliliter, which is the volume. But through core lab number 4, we know that density equals specific gravity. Therefore, the specific gravity in this case will be 3.0. So our answer to this question would be B, 3.0. Next question reads, which mineral property is found by scraping a mineral across a non-glazed porcelain tile? When we look at the different answers here, we have A, double refraction, B, hardness, C, luster, and D, streak. And when we looked at the different mineral properties, we said streak is the true color of a mineral when it is scraped across a non-glazed porcelain tile. So the answer to this question would be D. Example number 3 reads, explain how Mohs hardness scale and items of known hardness are used to assist in the identification of an unknown mineral. So if we had an unknown mineral and we wanted to test its hardness, we could use our objects of known hardness. We know a fingernail has a hardness of 2.5. A penny has a hardness of 3.5. Iron nail is 4.5. Glass is 5.5, and a steel file, has a hardness of approximately 6.5. So what we could do here is, if we had a sample of unknown hardness, we could use our fingernail, scrape across the sample. If it left a mark, then the sample will be less than 2.5. We could use a copper penny, scrape across the mineral sample. If it left a scrape, then we know it would be less than 3.5. An iron nail could be used to scrape the mineral sample. If it left a mark, then we know it's less than 4.5. And glass, same. Scrape the mineral sample along a piece of glass. If it left a mark, then it would be less than 5.5. And we can do the same process with steel file. The steel file, scrape the mineral, then we know it's less than 6.5. So by using all of these objects of known hardness, we can find the hardness of our unknown mineral sample. So if we look at the solution on the next slide, this solution outlines the process which I just discussed. We test the hardness by rubbing the objects of known hardness across the mineral. If it leaves a scratch, then it's less than the hardness of the known object. If it don't leave a scratch, then the mineral sample must be harder than the object of known hardness. And by doing this, we can narrow down the hardness of a mineral. Your turn. Take some time to complete solutions to the following questions. So you can pause your recording now to answer the following questions. Let's read through the following questions. First question states, a pencil lead contains the mineral graphite, which is composed of pure carbon, and a diamond is also composed of pure carbon. First question asks, how do their values of hardness compare on Mohs hardness scale? And the second question, part 2 of the question, reads, explain why a difference in hardness exists between diamond and graphite. If we look at the solutions, Part 1 states that diamond on Mohs hardness scale has a hardness of 10, and this is a higher value than the hardness of graphite, which has a hardness of 1, according to Mohs hardness scale. So if we compare diamond and graphite, diamond would have a higher hardness than graphite, which is a value known as 10, compared to graphite's hardness of 1. If we look at the two minerals, even though they're both made out of carbon, why do both have different hardnesses? And the answer lies in the properties that distinguish why mineral properties are the way they are. That is the strength of bonding between atoms and the arrangement of your atoms within the mineral. So diamond and graphite both contain carbon, but they have different hardnesses because of the strength of bonding between the carbon atoms, and also because of the arrangement of carbon atoms within the mineral sample. So to continue with the question, it says the carbon atoms in diamond are arranged in a tetrahedral pattern and exhibit stronger bonding, whereas carbon atoms in graphite are arranged in hexagonal layers with weak bonding between the layers. The high hardness of diamond on Mohs hardness scale in comparison to graphite is mainly due to the stronger bonding and the more stable atomic structure within the tetrahedra arrangement of atoms. So in conclusion, diamond has a higher hardness because its atoms are arranged in tetrahedrons, which are more stable, and also because of the strength of bonding between the carbon atoms in the tetrahedrons. They are very strongly bonded together. In comparison, graphite are arranged in hexagonal rings, which are located in layers of carbon atoms, and within the hexagonal rings and the layers, the bonding is fairly strong, but between the layers, the bonding is very weak. Therefore, the carbon atoms will peel off in layers, and this is what you see as you mark your pencil across paper, is layers of carbon atoms being released on the paper. Let's have another look at another example. Take the time and complete the following question. Solution will follow. Which mineral exhibits cleavage patterns shown below? If we look at the diagram shown below, we see a two-phase diagram. In the first, we see a whole bunch of layers that are stacked upon one another, and then we see an example showing that if we take the layers apart, we see strong bonding within the sheets, but weak bonding between the sheets. So which mineral to the right would show this one layer or one direction of cleavage planes between the layers of atoms within the sheets? Our choices are calcite, feldspar, halite, and mica. The answer in this case would be D, mica. Mica have their silicate minerals arranged in sheets, and between the layers of atoms that make up mica, we have weak bonding. Therefore, micas will split in layers and peel off as if like little layers of plastic peeling away from one another. So the answer to this question is D, mica. Summary. Let's look at an overview of the points covered in this presentation. The properties of each mineral depends on the following. Number 1, the type of elements present. Number 2, the arrangement of the atoms. Number 3, the strength of the bonding. In this case, the arrangement of the atoms and the strength of the bonding are key elements in deciding what the mineral properties of a mineral will be like. And the 4 mineral properties that these two characteristics depend upon will be specific gravity, hardness, cleavage, and streak. So if we look at these mineral properties, the specific gravity, hardness, cleavage, and streak, these are the four most reliable. These are your four most reliable mineral properties that all minerals depend on. If you take any sample of one mineral, for example, quartz, even though quartz come in various colors, the hardness, the streak, the specific gravity, and the cleavage, for any sample of quartz, regardless of what it looks like, its shape, its color, will all be the same. Same hardness for different quartz samples, same streak for different quartz samples, the specific gravity of different quartz samples will all be the same, and the cleavage for quartz samples of different hand samples will all be the same. So these are your four most reliable mineral properties when trying to identify unknown minerals.